Well, hi everyone. In this video, I'm going to talk a little bit about limits involving infinity. When we're talking about a function f of x, we can talk about the limit as x approaches a particular point c, and we can say that that limit of f of x is equal to a real number L if and only if we have this classic definition involving epsilon and delta. For all epsilon, there exists a delta such that if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. This is the classic definition when we have a limit of a function that does not involve infinity. So you notice that x is approaching a real number c, and the value of the limit is a real number L. But in this video, I would like to discuss what happens when we see infinity arising as part of the limit problem that we're looking at. Now, I'm going to just describe a couple of situations in this video. There are other extensions that we would need to consider as well, and I'll leave those to you. I'll try to mention what they might be. But let me write down two situations that I'd like to discuss in this video right here. The first one would be what happens if the L value happened to be infinity. So let's write that down. First of all, I'll call this Roman numeral 1. And what we're going to say is that the limit as x approaches c of f of x is equal to plus infinity if and only if, by definition, for all alpha greater than 0, there exists a delta greater than 0 such that if 0 is less than the absolute value of x minus c is less than delta, then f of x should be greater than alpha. So this should make sense. We've simply replaced the absolute value of f of x minus L less than epsilon with f of x needs to be greater than alpha. The rest of the definition is more or less the same. Now I'm going to invite you to pause the video if you would like and see if you can write down what it would mean to say that the limit of f of x as x approaches c is equal to minus infinity. It's a very similar definition to the one that I just wrote down, but I'm going to leave it to you to see if you can write that one down. The second situation, though, that is somewhat different is instead of changing the L value to infinity, what if we changed c to infinity? So in other words, what would happen if we wanted to write down a definition for the limit of f of x as x approaches plus infinity, and to say that that is equal to L? Well, by definition again, we can give another definition here, which is that for all epsilon greater than 0, there exists an alpha greater than 0 such that if x is greater than alpha, then the absolute value of f of x minus L is less than epsilon. So again, I think that this makes intuitive sense, and the definition is, of course, fairly technical, but I will invite you again to pause the video if you would like and see if you can write down what you think would be the definition for the limit of f of x as x approaches minus infinity to be equal to L. It's just slightly different than the one that I've put on the board here. So the first situation would represent a situation like this, where we might actually have a vertical asymptote on our function. As x approaches c from either the left or the right, the graph of f of x is as large as we want. So if I pick any alpha greater than 0 here, I can choose a delta. I can make a neighborhood around c such that all of the values of f of x are above that horizontal line where alpha is. That's the first situation. The second situation is quite different. The second situation is one where we are looking at what happens as x goes to plus infinity. And in this case, we might view the situation as being a horizontal asymptote at a y value of L. And maybe we have a function that's doing something like this. So f of x in this case is approaching L as x gets very, very large. So in other words, if I make a neighborhood around L here, right? So some horizontal strip that is sort of buffering the L value horizontally. In that horizontal strip, we can eventually find an alpha here that's greater than 0, such that all of the x's to the right of alpha have the property that f of x is within that horizontal strip. So it's really talking about two situations, the first of which is vertical asymptotes, the second of which is horizontal asymptotes. So hopefully these definitions make sense. Again, I would highly recommend for practice that you try to write down the natural modifications of these definitions for minus infinity in either of the places where we currently see plus infinity. And it's also possible, by the way, to talk about both the limit of f of x as x approaches infinity, but having it equal plus or minus infinity as well. So you can actually have infinities in both places. And that's also something that's worth investigating and trying to write down a definition for. So I'm not going to do all of that here, or we would be writing down definitions for 20 minutes, but at least we've got a couple of the main situations written down here, and I'd like to practice a little bit with these definitions. Let me give myself a little bit of room up here to write down an example for us to work on at the top of my board. So here would be an example. Let's see if we can compute with proof the limit as x approaches infinity of x divided by the quantity 2x plus 1. Now, in this case, you can try to come up with what the answer is before you prove anything. And if you think about it for a moment, as x gets very, very large, the plus 1 that you see in the denominator of this rational function becomes very insignificant. And you can almost think of this as if it was x on top and 2x on the bottom. In such a case, you would cancel those x's and you would get 1/2. And so the claim here, I'll go ahead and put it here now. The claim is that this should equal 1/2. You'll notice that we are in situation number 2 here, because we're talking about the limit as x goes to infinity, in other words, plus infinity. And we're claiming that the L value is 1/2. So I'm going to give myself some room now. I will erase these definitions temporarily, or at least the first one, so that I have enough room to sort of start writing down a proof of this claimed value. And in order to do that, let's read this definition again very carefully. It says for all epsilon greater than 0, which means I'm going to start my proof with let epsilon greater than 0 be given. And what I am tasked with here is coming up with an alpha that will satisfy this definition. In order to do that, what I'm going to do is maybe do some scratch work over here that I can then insert back into the proof momentarily. And in this scratch work, we ultimately are trying to understand how to get the absolute value of f of x minus L to be less than epsilon. And let me go ahead and feed in what f of x is. That's just a given rational function, x divided by the quantity 2x plus 1. And let me also feed in the L value of 1/2 right here. And I need to do a little bit of manipulation with this expression in order to try to solve for x, because I would like to figure out in terms of x what the alpha should be in order to have a valid choice to assume that x is greater than alpha. The first step, as you might imagine here, is going to be to find a common denominator. I'm going to increase my space to do the scratch work. The scratch work is really, of course, the key to the whole thing, right? Most of what's going on is really based along the scratch work. So let me find a common denominator in this fraction. And that common denominator would be 2 times the quantity, 2x plus 1. And in the numerator, I would then be left with 2x minus the quantity, 2x plus 1. So feel free to pause this video at any moment and make sure that you're comfortable with all of the algebra that I'm doing. So far, every single step is fully reversible. Okay, so this should look pretty good so far. And now the next thing I want to do is simplify that fraction a little bit. You'll notice in the numerator I have a 2x, and then I'm subtracting a 2x plus 1. If we want to bust out those absolute value bars, that's actually just 1. That's actually just 1. And then in the denominator, I can certainly take the 2 outside of those absolute value bars as well. So again, fully reversible in this particular step. I've simplified the numerator, and I've pulled a 2 out of the denominator. So I'm getting closer to being able to solve now for x, which is what I'm ultimately trying to do. Let's keep going. I'm going to move the 2 to the other side of the equation. So I will have 1 over the absolute value of 2x plus 1 less than 2 epsilon. And now I'm going to take a reciprocal on both sides, which will flip everything over. So the absolute value of 2x plus 1 would be now greater than 1 over 2 epsilon, like so. All right. And the next step is going to be a step that's only going to work backwards. I'm trying to isolate x here. And at the moment, what I need to do is remove those absolute value bars. So I can do that as long as I recognize that this arrow right here only works backwards. Now, backwards is the only thing I care about, actually, because I'm only going to be running this scratch work backwards, retracing these steps. And obviously, if 2x minus 1 is greater than 1 over 2 epsilon, then taking the absolute value of 2x plus 1 only makes the left side larger. So if it was already greater than 1 over 2 epsilon to begin with, then certainly after I put absolute value on the left-hand side, it only makes the statement more true. So I'm perfectly safe in doing that. And now I'm just going to add 1 to both sides and then divide by 2. So what will happen here is I'll get 1 over 2 epsilon plus 1 with a 1/2 in front of it. And this should be the value of alpha that we would like to choose. So let me go ahead now and come back to my main proof, which so far only has one sentence. Let epsilon greater than 0 be given. And now I'm going to pull the alpha seemingly out of thin air, but of course it really was derived using the scratch work. But I'm going to write it here as alpha equals 1/2 of the quantity 1 over 2 epsilon plus 1. By the way, you'll notice that that will definitely be greater than 0. So we are required to produce an alpha that's greater than 0. If for some reason you had some doubts whether this could be greater than 0 or not, you can always make tricks to force it to be greater than 0, such as taking the absolute value or adding something to it and just making it bigger up until a point that you're sure that it's greater than 0. But this one is already greater than 0 to begin with. So we don't have to do anything with that. And once we've proposed this alpha in our proof, all we have left to do is to check that it works. And to check that it works, I'm going to assume that x is greater than alpha. And that means I now need to verify that the absolute value of f of x minus L is less than epsilon. And that simply comes by reversing the scratch work. So retracing the scratch, we get absolute value of f of x minus L less than epsilon, which is exactly what we wanted. And keep in mind here that L is 1/2, as we had determined. So it's important that you try to figure out what the answer is ahead of time, even if you have not rigorously proven it yet, right? We need to think ahead, what will be this limit, so that we can make a claim based on our intuition or our rough analysis of the problem. But once we've made the claim, then we must rigorously verify it using this definition, right? Dotting all our I's, crossing all our T's, using the epsilon alpha definition right here. Feel free to pause the video and reflect on this. This is all you really have to write. The actual proof itself is very short, but you have to remember that there is a bunch of scratch work that was done in between. So I'm going to do a second example, but before I do that, if you would prefer to pause the video and make sure that you're comfortable with this, by all means, feel free to do that. Okay, let's try another example. And for the next example, I am actually going to use the other limit involving infinity. So I might recopy that definition down just so that we have it in front of us as we're trying to work this out. So let me remind you, the situation 1 was talking about the limit as x approaches c of f of x equals plus infinity. So I'm just recopying what we had written down earlier. This is if and only if for all alpha greater than 0, there exists a delta greater than 0, such that if 0 is less than absolute x minus c is less than delta, then f of x is greater than alpha. So let's take that definition and try to do another example. And here is the example. Let's prove that the limit as x approaches 0 of 1 over x squared is plus infinity. And I think that seems probably reasonable to us, yeah? As x gets very small here in the denominator, then this fraction blows up to plus infinity. That's basically what we would expect. So I'm going to try and do this proof. And I'm going to use the definition at the top of the board here. It starts off with for all alpha greater than 0. So I'm going to start my proof with let alpha greater than 0 be given. And now our job is going to be to come up with delta. And again, we're going to take a break from the proof to come over here and write out some scratch calculation to help us figure out what the delta should be, keeping in mind that ultimately, whatever the delta is, we want to derive the conclusion that f of x is greater than this given alpha value. So let me start like I often do by just plugging in what f of x is. You can see that that is just 1 over x squared greater than alpha. And from here, I'm going to try to get the absolute value of x minus c to show up in this work. Here, the c value is 0. So I really just want to come up with the absolute value of x in this whole thing. And I got my x squared right here. Let's flip this over again by taking reciprocals of both sides. That's a completely reversible step. So x squared now would be less than 1 over alpha. And at this point, I'm going to take the square root of both sides. And notice that since alpha is greater than 0, it'll make sense to take the square root of both sides here. So if I do that, so let's just write it this way. This is if and only if the square root of x squared is less than the square root of 1 over alpha. The square root of x squared is actually the absolute value of x. And so what we have is that the absolute value of x is less than the square root of 1 over alpha. And that seems to be fitting with this piece of the definition right here. I'm going to choose delta to be the square root of 1 over alpha. Yeah, that's it. So let's do it. Let's let delta equal the square root of 1 over alpha. And I just have to prove now that that delta works. So let's assume, let's take this second line of this definition on the right side and let's set up to verify that. Let's assume that 0 is less than absolute value of x is less than delta, which is the square root of 1 over alpha. And we don't really need to worry about this little piece of it. I mean, that's true. X is not going to be equal to 0. But the point is that the second inequality is landing us exactly over here in our scratch work. So we can take this and now, again, just retrace the scratch work. Retrace the scratch to conclude that f of x, right, f of x, which again is 1 over x squared, is greater than alpha, which is what we needed to prove. Okay, very nice. All right. So that's basically, in a nutshell, a nice example of looking at limits where the limit value is equal to plus infinity. I invite you to write down some examples of your own, maybe using minus infinity if you'd like, and see if you can prove them using a similar strategy to what I've shown here in these two examples in this video. I hope that they've made sense to you. Be sure that you're really working to internalize these definitions, right? We don't just want to have the intuition. The intuition is great. If you have the intuition that the limit of 1 over x squared as x approaches 0 is equal to plus infinity, if that intuition makes sense to you, if you can draw the graph, if you can kind of think about it numerically, that's all great. But ultimately, for a rigorous course in real analysis, we have to be able to use these formal definitions to prove these assertions that are based on our intuition. And so that's why I'm taking the time to really go through line by line with both the scratch work and the write-up of the proof to carefully present exactly how it should be written. Again, I hope it makes sense. Feel free to shoot me questions if it's not totally clear, or if you have any related questions to this, I'll be more than happy to try and answer them. Thank you so much for taking the time to watch this video, and I look forward to seeing you again soon in another video. Bye for now.